You got it, dude. Correct. Greetings and welcome, friends. Today we are continuing our look at the conic sections chapter, specifically targeting circles. But you may have realized, Mr. Waddy, we haven't talked about conic sections yet. And you're right, we haven't. So we'll start off by giving you a little definition of conic sections. It's the graph resulting from the cross section of a plane, all right, like a horizontal slice, and two right cones. So let me show you this little picture to explain this a little bit for you. So imagine I've got like two right cones kind of having their vertices touching like so. And if I do a horizontal swipe, whooshing, I would get a circular shape from a horizontal swipe through that Fruit Ninja style. If I swipe at a little bit of an angle, that circle is now going to be like an oval shape, right? And that's called an ellipse. If I swipe at even more of an angle, I might get what's called a hyperbola, and it's an interesting shape. We'll talk more about that later, but it ends up having two curves that are very symmetric to one another. And then if I swipe at, I believe, even more of an angle, I end up getting a parabola shape. So these are the four types of conic sections. Technically, there's degenerate cases where if you have it swipe right through the middle, you get a single point, or swipe right along this edge, you get a line, or swipe like right down vertically, you can get like an X or two lines formed. But those are called degenerate cases. We're not necessarily interested in those. We're going to talk specifically about the t'other ones is what we're going to be doing. So here's some definitions of circles and its related vocabulary. You don't have to write this down. You've seen it all before. So circle is the set of all points in the plane, two-dimensional, right, that are equidistant, the same distance from a given point in the plane. Good, good, good. And the name of that given point is called the center, and that distance, that set distance, is called the radius. So so as a little picture here, here's my little circle. That's a sad looking circle. That's good enough for me. So the center would be like here. This would be the radius. Here's the center. We'll actually end up later calling the center h comma k. And this would be the set of all points equidistant in a plane. And by the way, the definition for a sphere is very similar, except it's the set of all points equidistant from a given point in space. So in 3 dimensions, you would get a sphere. So if I just change this word to space, or in space rather than the plane, and yeah, you get the idea. So that's a circle. You've seen that stuff before. So let's talk about the equation of a circle. All right. So if it's talking about distance, this distance that's constant, called my radius, it turns out that the equation for a circle is going to relate to, who would have thought, the distance formula. Yeah, the distance formula. So let's kind of discover this. You don't have to write this part down. It's let the center of circle be C, the point C, h comma k, and the radius be distance r, and all other points be denoted x comma y. Now what's the distance formula? You might remember that's d is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared, right? You might recall that a little tad bit. So I'm going to just plug in my information here. So my distance is r, right? So I'd have r equals the square root of, and let's see, my points are the center and x and y. All right, so I'll have x minus h squared plus y minus k squared. And what they ended up doing with the equation of the circle, they were like, we don't like square roots and stuff. So to kill the square root, they decided, let's just square both sides. And that will be oh so lovely. Oh, so lovely. And the equation of the circle is the following. So let's see, here's the equation of a circle. And this is what's called in standard form. Just like with equations of lines, you might remember that, I'm getting a little bit of lag there. Whoop, whoop. Just like with equations of lines, you might recall that there were, you know, slope-intercept form, or...
I need to go back up, Tom.
But you didn't have to write that part. So, but with equations of lines, we had slope-intercept form, point-slope form, standard form. Eventually in pre-calculus, we'll talk about normal form and stuff like that. So in the equation of the circle, we're going to specifically today talk about two different forms for it. One is called standard form, like so, and the other is going to be called general form. All right, so for standard form, this is what it looks like: x minus h all squared plus y minus k all squared equals r squared. And the center is the point h comma k. All right, and the radius is the r there. Okay, so with that information, we're now going to be able to, you know, write our equations of circles, graph equations of circles, and all sorts of goodies like that. So let's do an example then, shall we? Little example, eh? Yeah, what do you say? I think I could fit a nice little example right down here. So, example A. Suppose this is what I've got. So let's write the equation of a circle with radius 2 and center -1, 3, and then we'll graph the circle. So if I'm going to plug things in this formula, just like with, say, slope-intercept form, you'd be interested in finding out what's the m and what's the b, so I could plug those values in. We're going to do the same sort of thing, except I'm going to plug in the values for r and h and k. Right? So based off of these facts, it appears as though r is the 2, and my h is the -1, and the k is the 3, right? So if I want to write the equation of this, I'm just going to plug this into this formula here. So I'm going to have x minus a -1, so that's actually going to become +1 because of the double negative squared, and then plus parentheses y minus 3 all squared, right, because the formula has the minus k, so it's the opposite of the y coordinate of the center. It's the opposite of the x coordinate of the center there. Equals r squared. 3 squared is 9. So this is actually the equation of the circle in that form. And just like with y equals mx plus b for lines, you were able to just look at that equation and instantly know, oh, this is my slope, this is my y-intercept. So hopefully eventually we'll be able to look at this equation and be like, oh, my center is at -1, +3, and my radius is the square root of this number, is what we'd end up gathering. What's up? Oh, blast. You got me. Yeah. I even labeled it, but I wasn't that good, so the radius is 4. Bam. Good save there, friendly friend. So if I want to graph this, let me show you some techniques for graphing. We're not going to do any crazy like rise over run stuff or nothing like that. But we're going to draw a little grid. Now let's think about where this is. So -1, 3, so that's left 1 up 3. So thinking about my coordinate plane, making sure I've got room for it. So I'm going to plot some of these points. So left 1 up 3, right there would be the center, right? And the radius is 2. And in order to draw a circle, this is typically what I do. I'll end up going up the radius, right? So 2 points above that, 2 points to the right of it, 2 points below it, and 2 points to the left of it. And that'll kind of give me 4 points to really get a general idea of what the circle's going to look like. And instead of trying to like draw this all in like one swoop, because chances are you're not going to do a good job at it, that's almost okay. I actually like to draw this in kind of like quadrants of the circle. So I'll draw one arc and then another. And even though the remaining points aren't necessarily perfect, it gives me a really good idea of where this circle is located, right? And So yeah, the idea is plot the center and then go north, south, east, west by the radius, and you're pretty good after that, right? So this is what the equation of a circle looks like. Thing I want to point out, the majority of conic sections are going to not be functions. You might recall that functions need to pass what's called the vertical line test, and notice that this does not pass a vertical line test because it hits at multiple locations for a single vertical line. So this is not a function. It is possible to graph this on a calculator, but you'd actually have to graph the top half and then the bottom half. But we'll talk about that later. Whoa, slow down there, friend. So there's our first example. Let's do another one, a little bit different. Yeah, that's fine. That's good. So let's, this time I'm going to give you an equation, and we're going to try to graph it. All right, so here I gave us the equation, and looking at this, just like we would with y equals mx plus b, I want to figure out what information am I looking for? I want to know the center and the radius. So what is the center going to be? Now remember, it's actually the opposite of those values, right? So x minus h, so h must have been positive 2. And y minus k, so k must have been negative 5. And then the radius is going to be the square root of this number, which is 3. Right, so that's the first thing you want to do is kind of label your pertinent information. And now let's try to graph this if we can. So let's see, I'm going to go over 2, down 5, so I'm primarily in like the 4th quadrant. So to plot this, let's go over 2, down 5. So here's my center, and my radius is 3. So it's actually pretty easy to graph these. So we'll go north 3, south 3, east 3, and west 3, right? And then I just kind of draw the curve that represents each of these, where hopefully all of the points on this curve, like hopefully this distance is also 3. And we just do the best we can, and that's fine. As long as I get these kind of significant points plotted, that's what matters. Good enough. And in the case of a circle, I'm actually not necessarily interested in what the y-intercept is, although we will later on in this chapter talk about how we could find the intersection of like a conic section in a line, for instance, or 2 conic sections. But yeah, so none of these points represent a y-intercept, none of them represent a slope. They just represent center and radius is the idea. So let me give you this new concept. So that's standard form for the equation of the circle. That's the helpful one, right? Just like y equals mx plus b or point slope form. The least helpful form for equations of lines was the standard form, you might recall. And standard form didn't have any information about the line in it necessarily. And similarly with general form, okay, of the equation of a circle. General form is when I just have no parentheses, and I've got all of my variables and everything, my constant, are all on the left-hand side of the equation, and it's equal to 0. So, what's up, Hank? Yeah, definitely, because general form is the other one we got to know about. So those are the 2 forms we'll be working with. Standard form has the parentheses, and it lets us know the center and the radius. General form doesn't contain that information, although it will still have its benefits later on. And the idea between D, E, and F, those are just numbers or constants. So they aren't variables for us. And D, E, and F, they will not represent your center. They will not represent your radius. So that would all just be coincidental if they ever did. They just happen to be numbers. Just like ax plus by plus c equals 0, which was standard form for the equation of a line. So here's general form. Let me do a recall. So my friends in class, you don't have to write this recall down. the skill set that you're going to need to be familiar with actually completely comes from completing the square. I just used complete there a couple times. So I want to do this recall concept just to make sure that we're awesome with the idea. So this is a Math 3 concept that we did. It also sometimes shows up in Algebra 2 classes or things like that. So here what we've got is an equation of a quadratic. This is not a circle. This is just a recall. And actually, if you were to graph this, this would be a parabola, oddly enough. So in order to solve by completing the square, let me walk you through this. Step 1 was move the old c term to the other side, right? So we remember doing that. Yep. And then we'd have x squared plus 10x blank equals 3 blank, right? So that's the first step we did. Now, the next thing we did was we wanted to figure out what would go in those blanks. And this was related to a perfect square trinomial pattern. A squared plus 2ab plus b squared is equal to, Jacob put the cell phone away, a plus b all squared.
Okay.
This is the perfect square trinomial pattern. It's equal to the square of a binomial. This is what we ended up doing back in the day. And this is going to be helpful for us with circles in a moment. So this is the skill that I want us to remember. So to find our new c term, does anyone remember the formula to find the new c term? The new c is equal to b divided by 2 all squared. So that's the little formula that you'll have to remember. So what we do to find my new c term, I'm going to take my b, the 10, divide it by 2 and square it. So that's 5 squared equals 25. So add 25 to both sides. And that is a legal math move, addition property of equality, right? It's not going to change the value of this. Now the benefit of that was the fact that x squared plus 10x plus 25, I have just now made into this pattern, right? I've forced it to be this pattern, and that means I can factor it super quick, like this. Question? No? All right. So in order to have it match this pattern, that means a must have been the x, b must have been the 5, because the square root of 25, or 5 squared is 25, and x squared is x squared, right, in order for that pattern to match. So I'm going to plug in x and 5 into this side of the pattern now. I didn't actually make you write down the a and the b last time. So x plus 5 all squared is equal to 3 plus 25 is 28. And now the benefit of this in solving quadratics was this worked for problems that were not factorable, and then from this point on you would solve by rooting both sides, plus or minus. You would have forgotten that, and you would have had x plus 5 equals plus or minus the square root of 28. Oh, 4 goes into that 7 times, I believe, and then you'd subtract 5 from both sides, and you'd solve for x, and you would get an exact answer, no decimals necessary, of this. And it's a wonderful thing. Square root of 4 is 2, and there's the square root of 7. So that's the skill we're going to need to know, not for the solving part here, but for the idea of how to complete a square and then make a perfect square trinomial so I can factor it.
We did this already, right?
That part we've done already. That's why it's a recall, yeah. So let's do our last example.
Yeah.
Here we go. Last thing. Example A.
Yeah.
So let's write the following equation, convert it from general form to standard form. So remember that standard form is the x minus h all squared plus y minus k all squared equals r squared. So that's what I want this to look like. But it's currently in general form. Right? That's too bad. So what we will do is some manipulation to this. And notice that this form has 2 squares of binomials in it. 2 of them. And notice that completing the square from a moment ago gives me the square of a binomial pattern. So what that allows us to do is we're going to double complete the square here in order to get these two perfect square trinomials that will give me squares of binomials. Now the first thing I'm going to do to simplify this, I'm going to divide by 2. All right, I'm going to get rid of these 2's here. Anytime I have that, that's a no thank you. So let's just make those positive. And in fact, if I wanted to do some more advanced completing the square problems with you guys, you might have remembered that we never completed the square with a leading coefficient. So I'm going to divide everything by 2, and I'm going to pull my x's together, my y's together. All right, so 2x squared divided by 2 is x squared. And let's get the other x over here too. Negative 4x divided by 2 is going to be negative 2x. And I'm going to leave a blank there. And then let's put the y's together now. 2y squared divided by 2, that's just going to be plus y squared. And let's see, here's the other y. 12y divided by 2 is plus 6y. And I'm going to leave a blank. And 18 divided by 2 is 9. It's negative. To save us one step, technically it would have looked like this. We're going to add 9 to both sides and just make it equal positive 9. All right, so I'm moving that negative 9 to the other side. And then, ready for this? Blank, blank. So,
Yeah, I bet this one too.
so, here we go. I'm going to have to double complete the square. So I want to make this a perfect square trinomial and this a perfect square trinomial. How do I do that? I need to find my new c, which is equal to b divided by 2 all squared. So for the x's, I'm going to be interested in taking this, the b term of that quadratic, so to speak, divide it by 2 and square it. So let's do that. So negative 2 divided by 2 all squared. Oh, looks like my battery is dying a little bit, but that's all right. All of us are dying slowly. It's kind of sad. Equals 1. So I'm going to add 1 here. And 1. But if I'm adding 1 on the left-hand side, I got to do it on the right-hand side as well.
Yeah, I don't know what exactly.
Well, yeah, just keep following along. Practice makes perfect. Sometimes you have to step out in a little bit of faith with mathematics. You actually will understand after lots of practice. Usually you don't understand prior to that. So that's a common thing. So, yeah. So let's complete the square for the y's. So Hank, how would I find what goes here? What formula would I use?
The new C formula, right?
Yeah, the b divided by 2 all squared.
Thank you.
And as Kirsten was saying, that's going to be 6 divided by 2 all squared equals 3 squared equals 9. So I'm going to add 9 to both sides. So notice what I've done. I've just double completed the square. Doubly completed, right? That's all we had to do.
So we're done now?
Incorrect, because that still doesn't look like standard form for the equation of a circle. I think we would agree, right?
Why are you standing up?
I'm just,
He's dying.
I'm dying.
Slowly.
Slowly.
There it is.
So here we go. I'm back. I got my juice for my tablet. So so I want this to look like this. That means I'm going to have to factor this part and factor this part. Now to factor this is going to look like something all squared. The y's are going to look like something all squared equals 9 plus 1 is 10 plus 9 is 19. All right. So what does this inside look like? What's that going to come from? Well, it's going to be an x, and it's going to be whatever it was before I squared it. Do you guys remember that little shortcut?
Yes.
It's negative 1 there. What's going to be in this parentheses?
Y.
Y and a positive 3.
Plus 3.
And look, I now actually have this in standard form. So the benefit of it being in standard form
You don't have to do anything else.
is what is the center?
1 negative
1 negative 3.
1 negative 3. Good call on the opposite, remember? So, yeah, good job, good job. And for r, is the radius 19?
Yes. Now it's 8. Now it's the square root of 19.
Right? 19 is equal to the radius squared, so it must be the square root of 19. right? So I could graph this if I wanted to. I'm not going to have us do that. The square root of 19, by the way, is approximately 4.3589. So if I wanted to graph this, I would plot the center going over 1, down 3, and then I'd go north, south, east, west by that many points, plot those 4, and draw my circle. That would be the idea. So thanks for watching, Internet friends. We'll spend another day on circles tomorrow. Have a great day. Bye-bye.